Hello students, welcome to another tutorial on static equilibrium. In this tutorial, we determine the maximum force that the bicep exerts on the forearm. Now what we're given is a few conditions. I hope you guys had time to go through the question, practice it out. Whether you struggle or you manage to work it out, I always advise that you try out the question before watching the tutorial session. Now, even if you find the correct answer, it's still best for you to just watch the tutorial, just for you to get one or two alternative means of getting the answer. That is always beneficial for to everyone, of course. Now let's get right ahead to how to work out this question. Now, as I always do, the first step is to draw the entire system, but now only showing the forces acting on the system. Now, since the forearm is going to be in equilibrium, the forearm and hand are together, they're going to be in equilibrium. We're going to take the fact that the sum of the torques about any point on this system is going to sum up to 0. So if we drew the system as just a free body diagram, what would have is we can just picture it as just a line, a horizontal line. Now, what the question points out for us is, I want you guys to be very careful here. You see, the forearm kind of rotates about the elbow, but the bicep is attached some distance from the elbow. It is attached about 5 centimeters from the elbow. So what we notice here is that, let's take this as our elbow, the point about which the forearm is rotating. So what we see now, or what the question tells us is, the bicep attaches itself about 5 centimeters from that point of rotation. So let's say the bicep goes up. So this is supposed to be a straight line. Let's draw it better. So we have something like this. Now let me use a different color for forces. Okay, now, so what we're saying here is the bicep attaches itself some distance away from the pivot. So we're taking the point, the elbow as our pivot, since that's the point of rotation. So this is 5 centimeters. Now, yeah, you can work with the centimeters, it will still come out fine. But I always advise students to stick to the SI units. It kind of avoids the issue of knowing when it's okay to work with any units and when you actually have to work with the SI units. So just stick to the SI units. So if we convert 5 centimeters to meters, of course, you guys should know already how to convert that. You just dividing this by 100, and this will become 0.05 in meters. Now, the next thing that the question tells us is, if we go back to our diagram, if we're to take the mass of the forearm and the hand to combine, they have a combined mass of 2 kgs. Now, let's say somewhere here, this is where the weight of the hand and forearm, this is where they act. So it means that we have a downward force due to their weight. Now, again, to calculate this weight, remember we have to multiply the combined mass by 9.8. This is what gives us the weight of the forearm and hand together. And of course, if you work out this, you get the weight as so you get the weight as 19.6 newtons. Now, again, this is the weight of the forearm and hand. Now, if you go back to the diagram shows a mass that is in the hand. Now, this is not part of the 2, of course, it can't be, that's the 25 kg. It's not included. The 2 kg is just the forearm itself and the hand here. So not what is in the hand. So in this case now, we have to take note that at the far end, not really at the far end, just at some point somewhere here, we have an object that is in the hand that is being held, and this object kind of exerts a force on the hand. This is a force due to the weight of the object, and it is a downward force. So this force is equivalent to the weight of that object. The object has a mass of 25 kg. So if we want to get the weight from the mass, just multiply the mass times 9.8, the gravity. So remember, weight is equals to mg. So the mass 25 kg times 9.8. Here we get the weight of the object as, that's 245 newtons. So if we look at our system, these are the forces that are acting on the hand and forearm. Now the question is, since the system is in equilibrium, what we're taking from this, since it is in equilibrium, it means that the sum of the force of the torques must equate to 0. Now, having drawn the free body diagram showing the forces, the next thing that you want to check is whether the forces and the distances are perpendicular, or if you need to do some manipulation here and there. So if we start with the 245 Newton force, we see that here they are perpendicular. The hand forearm system is horizontal, the weight is vertical. So we get that perpendicular relationship. So this is fine. Now, how about here? Here also, the weight of the hand and forearm going down, and the system, the distance we're going to use is going to be from the pivot going down in this direction. The distance is going to be perpendicular to the force. So this passes as well, they're perpendicular. But then we have a problem. You see, we want to find F max here, the force due to the bicep. But then this force is at an angle. The question gives this angle as 105 from the horizontal. Now, we can't use that. We want the force to be perpendicular to the distance. Now, since we're going to use this as our distance, we kind of need this force to be perpendicular to this distance. And how does perpendicular to the distance look like? Well, it looks like this. This is a line drawn that is perpendicular to our distance. Now, in this case, it means that we take this as a y-axis, and we take the line along the distance as our x-axis, implying that we kind of have to resolve this force to get its vertical component or its y component. Now, to do that, we need the angles. Now, of course, we know from here up to this line, it's 90 degrees, and if the whole thing in black is 105, it implies that this small section here is equivalent to 15 degrees. Okay, now knowing this, we can easily get the y component of Fm, the maximum force. So of course, the two are adjacent. You guys are very comfortable working out vectors, getting the components. If you're not, I will leave a link in the description to my video on vectors, how to get the components. So of course, if you were to follow the instructions on how to get the component of the vector, you guys should see that if I label this as Fm in y, you guys should see that Fm in y comes out as Fm itself multiplying cos 15. Now it is going up, so we expect this to be positive, so that's fine. Now we've got the force. Now what we're going to do here is we're going to eliminate all the other forces that we don't need, and leaving only the forces and their corresponding distances, the ones which are perpendicular to each other. Or rather, instead of rubbing on that diagram, let me just draw a new one. So what we have is the system, the horizontal system, and apart from this, we have the 245 Newton force going down, perpendicular, so this is the path. And then again, we have the weight of the system, that is 19.6 Newton, going down. Again, here we have perpendicular. And lastly, we just saw that this, let me draw it with a different color. So we just saw that we have the component of the force from the bicep, also perpendicular, but this is given as Fm cos 15. And this is perpendicular now. Okay, now we're taking this point, the elbow as the pivot. Now, what are the distances? If we go back to the question gives the distance from the elbow to where the force Fm is acting as 5 centimeters. So this is 0.05. And then from the elbow to where the weight of the hand and forearm is acting is given as 15 centimeters. And lastly, where the mass is, the one in the hand, is given as 35 centimeters. So if we take those lengths, those distances, we observe that we have from here up to there, that's 0.05 in meters. And then from here, from the pivot up to the weight of the hand and forearm, we have 0.15 in meters. This was 15 centimeters, 0.15 in meters. And lastly, we have from here, we can draw it down from the elbow all the way up to where the weight is. This is given as 0.35 in meters. Now, the last step now, this is now where we're using our formula. So the sum of the torques is equals to 0. So remember, torque is equals to force times perpendicular distance. We've already seen that the forces and the distances here are perpendicular. So it's now just a matter of calculating the individual torques, bringing them in our equation, and then working it out. So the last thing that we want to do before we use our equation is to identify the forces that are the turnings that are clockwise and those that are anti-clockwise. So you guys should be able to observe that blue is causing rotation, clockwise rotation, and red, Fm cos 15, it's kind of trying to cause the system to rotate in an anti-clockwise manner. So if we work it out, then what we see is anti-clockwise, it's Fm cos 15, that's the force, times the distance. What is the distance? The distance is given as 0.05. This is anti-clockwise, so I'll take anti-clockwise as positive. Now clockwise, we come to this torque. This is in the clockwise manner, so it is negative, and the force is 19.6. The distance is 0.15 meters. And then the other turning effect, that's 245, the force, multiplying the distance, that is 0.5, 0.35. This is what equates to 0. So if we simplify this, what we have is Fm cos 15 multiplying 0.05. So let's take like terms to the other side of the equation. So what we end up with when we multiply 19.6 and 0.15, so we can multiply this. So we multiply these two, we get 2.94 plus, and then we multiply this side, we get 85.75. So the next step is now just to add these and then divide by that. So if we did that, so let's maintain the left hand side first of all, that's Fm cos 15. And then this is multiplying 0.05. This is equal to the right hand side, we can add them. We get 88. That's, yeah, we get 88.69. We divide by cos 15 times 0.5. So we get Fm. Then this is 88.69 divided by, so when writing this, so it's better to start with the number. It's preferred to start with the number, and then you have, of course, the angle. This kind of avoids an error of having to mistake what is under the cos and so on. So from here, you can then simplify, and you guys should be able to see that Fm comes out as 1,836 newtons. So this is how it comes out, or you can write it as, if you want three significant figures, you can write it as 1.84 kilonewtons. Yeah. If you want to write it in scientific notation, this comes out as that's 1.84. So move decimal place 3 times, so times 10 to the power 3 newtons. So any of these, you can present it if you want to significant figures. So you can write it like that, or you can write it like this. All right, you guys. So this is how you go about this question. In the next video, we're going to introduce properties of matter. It's just going to be a brief description. And then after that, we're going to work out a lot of problems as always. So this topic that we're looking at has, as always, a lot of applications. And most of these questions were actually application questions. I hope you guys were able to find this series enjoyable, relate to, and so on. All right, otherwise, we'll see you in the next video. This was your tutor.